The question Michel addressed is very important and basically links many of the issues we heard. Can you hear me? Yes? Okay. So the Aisys Flow-I, VitaQ, Zeus. I want to say that the Flow-I also has automated gas control. So there's a new addition to the family. How they work and how close they are. This is not a contest. There's 100 ways to Rome, and there is no right or wrong. I reiterate, all these machines do a great job of reducing anesthetic agent usage. I have no conflicts of interests. I have learned a lot from all parties involved with inhaled anesthetic delivery, and I have been impressed with the passion engineers and their teams display about their inventions. And this is a passion I share. Okay. That being said, this is the title, actually, ramp functions, the crossroads. And what I mean with that is, we heard Michel talk about PK/PD. I have a lifelong interest in quantitative aspects of low flow anesthesia. And we have technology, the machines I'm going to talk about. And really, I want to focus on the rate of rise, the ramp function, which really brings all these things together. How do these machines address the first 5 to 10 minutes of agent delivery, and how does that translate into how much agent they use? Again, the previous speakers have made it very easy to define the ramp function I'm talking about. This here is the opioid axis. Here, what is actually, let's see here. So the opioid axis, the hypnotic axis, you give your IV induction, and you get to a certain isobol that's adequate for endotracheal intubation. Okay, then patient is intubated, and obviously the concentrations of the propofol and the opioid will decrease. But what I do not want to happen is that the combined effect of the propofol and the opioid results in a chance of patients becoming conscious. So I want 99.99% of the patients to be unconscious. So then the question becomes, I'm going to add some sevoflurane, but how fast does the concentration have to rise? Which ramp function does the patient need? Does it have to be something like this, something like that, something like that? Do you want to add a bolus of propofol? And what's the trade-off in terms of agent usage? The periods after induction, when the effects of IV agents are waning and inhaled anesthetics concentrations are increasing, constitute a unique and complex pharmacological challenge, just like Michel just told us. Which ramp function the patient needs is a deceivingly complex question. Yet, when you use an automated low-flow anesthesia machine, you are going to have to enter a number, an ential. And you have to know that this has ramifications for the depth of anesthesia and for agent usage. So now let's go ahead and see how the different machines at this time implement this. Throughout the remainder of the lecture, I'm going to show you data on patients that underwent abdominal urological or GYN surgery with a target sevoflurane concentration of 2% in oxygen and air, just because I have a lot of data on 2% ential with the different anesthesia machines. So, if you look at patient uptake at 2%, how much does the patient actually take up? Well, between 5 and 60 minutes, it's 5.15 milliliters of liquid sevoflurane. Between 15 and 60 minutes, it's about 4 milliliters. And what I'm going to do is progressively fill up this table towards the end of the lecture, and I'm going to show you the sevoflurane usage with the different automated low-flow anesthesia machines. And the first 5 minutes are particularly important with regard to agent usage. And that's where the importance of the entitled function comes into play. Player number one of our automated low-flow family is the Aisys. What does the Aisys do? Well, you set the target you like for your patient here. For example, 50% oxygen entitled. You decide to use the minimal flow, the lowest flow in the auto mode, with the Aisys is half a liter, and your target at 2%. The machine measures the end tidal concentration using the gas analyzer. It's being placed into an algorithm, and then the machine will adjust your vaporizer and fresh gas flow settings for you to get to the desired end tidal concentration. Now, how to prime the system with 2% sevoflurane? You want to have 2% sevoflurane in the system in and by itself. Let's say that the circuit volume and the lung volume of the patient combined is 6 liters. If I want to fill this up with 2%, I need 120 milliliters of vapor. But I want to keep the system closed. Now, patient uptake of oxygen is 180 milliliters per minute. So, if I want to keep the system closed, I should not give more than 180 milliliters per minute. So the question becomes, how do I give the 120 milliliters of Sevo together with the 180 milliliters of oxygen? Can we do this without preventing excess gas from leaving the circuit? Or said differently yet, what vaporizer percentage do we need to get 2% in the system with 180 milliliters per minute? Well, obviously, it depends on when you would like to have the 2%. And that's where we're starting to talk about ramp functions. If I want to have 2% in 1 minute, I'm going to have to add the 120 milliliters of sevoflurane to the 180 milliliters of oxygen, which combined is 300 milliliters, so 120 milliliters vapor in a total of 340%. Problem, our vaporizer only goes up to 8%. Maybe I can wait 2 minutes, then I have 360 mLs of oxygen in which I can put 120 of Sevo. Well, then I need a vaporizer that gives me 25%. No can do. And we can go on like this. And you see, it's only after 8 minutes that the vaporizer will get you to 2%. And that doesn't even include the amount taken up by the patient. Now, this is a study that Wim Powell's presented a few weeks ago in Louvain. And what this graph shows you are actually all the fresh gas flow vaporizer dial setting combinations that allow you to reach an end tidal of 2% after either 2, 3, 4, or 5 minutes. So that's an empirical model we built. Now, the vaporizer only goes up to 8%. So, if we would like to have our end tidal to 2%, then we can use all these fresh gas flow vaporizer dial settings, here the pink line, if we want to have the 3%, if we want to have the 2% at 3 minutes. But what does the Aisys actually do? The rate of rise of the end tidal is the same regardless of the fresh gas flow you select. And the implication, that means that even though you are telling the machine use a certain fresh gas flow here, 0.5, 0.75, 1 or 1.5 or 2, the machine will actually override your fresh gas flow settings. It will tell you, I'm first going to take care of the end tidal concentration, and then I'll take care of the fresh gas flow you're asking. And the average fresh gas flow that the Aisys is using in this particular setting during the first 5 minutes is 1.5 liters, because the amount of sevoflurane used is the same regardless of the fresh gas flow you selected. So that's the same thing here. Fresh gas flow is selected by the user, but the Aisys will say, I'm going to first get you the end tidal, and then I'll lower the fresh gas flow. Could we increase the vaporizer output? Yes. Why? Because at 20 degrees, the vapor pressure of sevoflurane is 160 millimeters of mercury. That's a physical given. So 160 millimeters of mercury is 21% of atmospheric pressure. So yes, we could give a lot more sevoflurane. So let's get back to our graph here. If we would make the vaporizer and let it go all the way to 20%, you can see that you will get your end tidal with a fresh gas flow within 3 minutes, with a fresh gas flow of 180 milliliters per minute. So you could use 180 milliliters per minute and get your entyral up to 2% within 2 to 3 minutes. So that a long story just to be able to fill out this little box here. So the Aisys uses 2 to 3 milliliters the first 5 minutes and 8.1 milliliters during the next 55 minutes. The references the references can be found in the right lower corner. Now, a bonus you get by the fact that the Aisys is using the 1.5 liter per minute during the first 5 minutes is that you actually, regardless of your fresh gas flow selection, will rapidly go to your target oxygen concentration. Could we choose a different ramp function? Could we add propofol while the entyral is rising a bit more slowly? These are genuine questions. I don't have the answers. Michelle today has just started to lift a little bit. She's starting to help explain these questions, I think. Let's move to the second member of the automated low flow family, and that is a different animal. Now, interestingly, the rate of rise of the Zeus is exactly the same as that with the Aisys. It's exactly the same. Yet the Zeus differs because the Zeus really has separated agent injection here, liquid injection, from carrier gas administration. Those have been uncoupled. So it actually allows the machine to inject the liquid separately from the carrier gas. And if this would be 6 liters, you'd need 0.66 milliliters of liquid to get to your 2%. So that actually allows the circuit to work fully closed. And in addition, you have the blower here, which rapidly circulates the fresh gas flow, and that'll get the entyral concentration to rise rapidly to the desired concentration while maintaining the system closed. And closed the system is. We placed a large bag at the exhaust of the Zeus and measured exhaust for an hour, and the amounts that are wasted are really marginal. So this allows me to fill out these numbers here. You see that the Zeus uses 5.15 mLs and 4 mLs in the time intervals stated above. And this really matches patient uptake. For a variety of reasons, interestingly, I cannot tell you yet what it uses during the first 5 minutes. That is beyond the scope of this lecture. Another trick that the Zeus uses to maintain a closed circuit is that it allows the concentration of oxygen to drift very gradually to the target here over 15 minutes. And that's a pretty smart move, because in doing so, it allows the circuit to be closed. How does the machine do it? Well, after your pre-oxygenation, the machine here will give only air for a while, 180 milliliters of air, and the oxygen will be gradually replaced by nitrogen. And it is only after the target oxygen concentration has been reached, here at 15 minutes, that the machine will switch to oxygen. If you add up those two, you get the total fresh gas flow. And this actually gives you the average uptake of a patient, the average oxygen uptake of a patient under anesthesia, and that is 180 milliliters per minute. We have a new addition to the automated low-flow anesthesia family. It's the flow-eye. That's the heart of the system here, I think, or part of the heart of the systems. These are carrier gas delivery systems that in and by themselves act as a ventilator. So here your carrier gases come, vapor is injected, and everything is pushed towards the patient. Previously exhaled gas will be added to the mix by a fourth ventilator using oxygen. So oxygen is the driving gas, and will push the previously exhaled gas towards the patient. So that is how the flow-eye works. So that's an injector. And this here is the volume reflector, which is a physically open, functionally closed system. Let's have a closer look here. As long as the fresh gas flow is higher than the patient uptake, some of the exhaled gas here will move into this very long piece of tubing towards the end and be wasted. once the fresh gas flow is lower than patient uptake, this here, this point, this is the intersection between the exhaled gas and the driving gas of this part of the ventilator, it will move backwards. And this is actually a very sharply defined surface. There is not a lot of mixing there. So this is the automated gas control system, and obviously you have the same options as with the other machines. You can select your target, oxygen and CO concentration, your minimal fresh gas flow, which currently is 0.3, but it has an additional tool. It allows you to select the rate of rise. Hence my interest in ramp functions, and that's why I asked Michel to talk about it. You have a range of 1 to 8, slow or fast. So you set your target for your patient, and then you then you say to the machine, I want to get there fast or I want to get there slow. And I'm going to go to the ramp function again. So this was the Zeus, this was the Aisys, and actually for the flow eye there's a host of different curves, because you can select the rate of rise. They all go to the same interval. But you see for the flow eye, you have different ramp functions depending on the speed the user selects. Interestingly enough, the fresh gas flow that the machine uses is the same regardless of the speed you're using. It starts off with 18 to 20 liters per minute, very short-lived, decreases exponentially towards 0.3 liters per minute after 15 minutes, regardless of the rate of rise you select. But despite the fresh gas flow being the same in all the speed groups, the slower speed here reduces agent, that's the slower speed, reduces agent consumption after 10 minutes by 100%, from 4 to 2 milliliters of sevoflurane. After 15 minutes, agent usage is the same, and that's logical because the fresh gas flow has decreased to the 0.3 liters per minute. Now let's plot these numbers in the table, and obviously for the flow eye you won't have a single number, you'll have several numbers depending on the speed you selected. And I'm going to let these numbers kind of speak for themselves, but I want to again point out how important agent usage during the first 5 minutes is with regard to overall consumption, which will actually be my last slide in just a few minutes. So the question now, before proceeding, the question is, are these ramp functions acceptable, these rates of rises? Do we get into any valleys of no anesthesia? And we're just starting to be able to study this with Michel's model. But I hooked up a BIS monitor because I was really very curious. So I selected a target end-tidal concentration of 2%, and I arbitrarily selected a speed of 2, 4, and 6. That's speed 2, end-tidal reached after 5 minutes. That's speed 10, speed 4, end-tidal reached after 10 minutes. And that's speed 6, end-tidal reached around 30 minutes. The induction had been done with propofol, 2 milligrams per kilogram, and 7.5 to 10 micrograms of sufentanil. And so these are the BIS values after this. So the patient was intubated, then the system was connected, and the flow eye started doing the thing it's supposed to do. And then you can have a look at the BIS values. Actually, if you analyze the BIS values, there are no differences between the three groups. Of course, you want to have a look at the outliers here, but I think these are all pretty acceptable. So I think this is a great area for research, which we're just starting to uncover. What about the oxygen concentrations? The oxygen regulator is not controlled by the speed option. You will get your target oxygen concentration within minutes. Within minutes. And how does a machine do that? Oxygen always comes first. It gives you a very high, very short-lived fresh gas flow of oxygen. So you very rapidly go to your oxygen, but you have barely injected any sevoflurane. And we're talking here about 10 to 20 seconds. Okay, the future. This one is looming around the corner. It's going to be member number 4. It's the VitaQ under development. It's going to be a closed system using liquid injection with, in addition, active charcoal, which will allow the machine to remain closed when you want the entitlement to go down. With the other machines, you have to increase your fresh gas flow. It will have a xenon option, and I hope we'll be able to give data in the future about this machine. So that kind of summarizes it. This data will all be available on the web next week. I'm going to ask my brother to put it on there, so no need to chart it down. But that's my final slide, basically. You can see two numbers here for the Zeus. That's because I'm still figuring out whether there's a difference for the Zeus between the reported milliliters of sevoflurane you used and what we get when we weigh the cassette. But this actually tells you what the implications are of a selection of a ramp function with regard to agent used by the different anesthesia machines. So, again, the period after induction, when the effects of IV agents are waning and inhaled anesthetic concentrations are rising, constitute a unique and complex pharmacological challenge. If you use an automated low-flow anesthesia machine, you have to choose a number, and it has implications with regard to depth of anesthesia and agent usage. Again, these are all beautiful machines. They all reduce agent usage to a great extent. There's a different ways to roam, and I look forward to a further extension of the family. Thank you.